Thanks, Ching, and thanks everyone for coming to hear this next tutorial. There's a lot of more interesting stuff in store for the rest of the day, so I hope you'll continue to attend the sessions in the afternoon as well. Just a quick disclaimer that I hate to have to make. I'm nursing a bit of a cold these days, and so if I need to take a pause in the middle of the talk to drink some water, I apologize in advance and hope it's not too disruptive. So like Ching said, with this the next few lectures here, we're going to start talking about deeper models, still through the lens of low-dimensional structure. I just realized I think I don't have the clicker. Did I need a clicker? I'm a little bit stuck. Do I have that? Thanks, sorry. Thank you. Okay, so getting into deeper models, but first let's recap a little bit of what we heard about in the lectures this morning from John and Yuchen. So the first lecture where John introduced some of the canonical low-dimensional signal models and computational toolkits for working with those. In that case, maybe the most simple instantiation of those principles was the sparse recovery problem, where we have a low-dimensional signal, which is sort of sparse, but the structure here is all sort of linear or piecewise linear. We have linear measurements. The computational toolkit that we have for reconstructing or computing with these signals is that of convex optimization, efficient, scalable, all that good stuff. And we can even obtain, in many cases, provable guarantees for these algorithms, where the types of results that are representative of what we get, say when we have enough measurements of the low-dimensional signal, where enough here depends on intrinsic structural properties of the data, here measured through its sparsity, we can reconstruct efficiently using these convex optimization problems. Then going forward, where we wanted to be a little bit more flexible in the models that we have, in Yuchen's talk, we started to look at cases where we simultaneously learn the low-dimensional representation and the model itself. So in problems like dictionary learning, in order to have this flexibility, we needed to move away from the convex toolkit and start using non-convex optimization, which at first is scary, but as we learn in a lot of these very naturally occurring machine learning signal recovery problems, we can still have the same types of efficiency and recovery guarantees that we saw in the convex case, even using sort of local non-convex optimization algorithms as our computational toolkit, where the types of results we get again say that we can succeed when we have, in this dictionary learning case, measurements that depend on, again, intrinsic structural properties of the data. And so what I'm going to start talking about here, and what we're going to visit in the rest of the tutorials throughout the day, and indeed in the rest of the talks throughout the workshop itself, is where is the low-dimensional structure? How does this all play out in the more modern setting where we're now computing with deep learning models, going from where we had previously looked at linear measurements, bilinear measurements in dictionary learning. Now we have a sort of staggering degree of nonlinearity in these models. We're using, working with a variety of tasks here, but maybe in a very simple supervised case, just taking a network that has some parameters that we're trying to learn, using data sets, and so these networks will map data to outputs, maybe labels for classification. And this mapping now from parameters to the outputs of this network is sort of very highly non-convex, and it's not always the case that we have the same sort of structured, nice non-convexity that we saw in some of the previous models. So we want to understand here is, to what extent low-dimensional structure in the data and in the network itself, perhaps, is allowing us to understand, train these models, succeed on practical tasks. So where exactly and how exactly does low-dimensional structure play a role in the practice of deep learning, especially modern deep learning, where nowadays we have some pretty exciting, at least demonstration level sorts of AI tasks where we can see these models working. And so what we're going to see, and in my talk and the rest of the talks throughout the day, is that low-dimensional structure is still playing a massive role here once we sort of tease it out and identify exactly how it's playing a role here. And so I'll start off by doing a quick survey, just some sort of vignettes in the style of the talks previously, that are attempting to get at what exactly are the low-dimensional structures present in modern data sets that maybe demand or befit the use of these highly nonlinear deep learning models for computing with the data here. So I'll talk through a few simple examples there, and then once we have some idea of what the specific low-dimensional structures in data are, we'll try to tease out a mathematical model problem that we can study a bit try to get some insights similar to what we had for the convex and non-convex case for sparse recovery and dictionary learning, where we can understand resource trade-offs in between properties of the network, the deep networks that we're training, and then structural properties of the data once we've suitably formalized things. After me, so when we come back in following lunch, MBZUAI will give us some discussion where we'll start to not only look at deep learning from sort of a data and model perspective, but begin to open the black box of this model a little bit, try to understand what is being learned and the weights or the features of these neural networks, and get a handle on that aspect of the problem. And then going forward later in the afternoon, Professor Ima will be telling us about when we have specific low-dimensional structures present in data sets, maybe even how we can design end-to-end white box networks for computing with them in under various notions of optimality. And of course, we'll see other talks as well, going more into applications in imaging, as well as a deep dive into sparsity in neural networks. So to start off, I'm going to talk through a few motivating examples of low-dimensional data that seems to demand the use of deep learning. And we're going to try to explore a few basic questions throughout these examples. So those two questions are, what will be an appropriate mathematical model for the types of low-dimensional structure that's present in these applications where we're using deep learning? And sort of how does a sort of reckoning and accounting of the low-dimensional structure that's present in these types of problems give us insights and even allow us to make practical improvements to sort of improve the deep learning approaches that we're using. So the first task I'll talk through at this point with some of the demonstrations that we see these days, text-to-image, photorealistic generation. Now we even have 3D scenes and videos being generated. So image classification, which I'm going to talk about here, can feel a little bit quaint. But in many ways, this is now perhaps a classical problem that has led to a lot of innovations in deep learning in terms of driving progress in architectures through optimization on benchmark data sets. So basic image classification task, I'm showing here we have a couple of non-orthogonal classes, which will appear a few times in this talk. We're trying to decide whether a given input pixel image contains as its content a hedgehog or a hairbrush. So the data space here is just the images. The outputs are going to be, for this binary case, maybe a +1 if we have a hedgehog and a -1 if we have a hairbrush. And we're interested in just training a deep neural network using some generic statistical learning loss in order to classify these data. And so the main question we want to have here is maybe why is it that we are often using deep models when we're computing with image data instead of more classical linear classifiers or kernel classifiers? And so if we think about the types of variabilities that are present in natural image data, we can get a little bit of an intuition for why we might need or why it might be most beneficial to use these very flexible deep models here. So natural image variability is sort of notoriously complex, and we can identify a few distinct different modes of it here. Deep learning sort of seems to give us a good tool for coping with all of these. So statistical variability, sometimes called that, can just be referred to variability, or can just refer to variability associated with different classes that is kind of a probabilistic type of variability. So something like the class of dogs being subdivided into several different dog breeds, and even different dogs themselves within the same breed having sort of variabilities in their appearance when we have images of them. This is pretty hard to cope with analytically, and this type of sort of a lot of the progress that we've seen in the last 10 years of deep learning has maybe been using these very flexible architectures and a very data-driven approach to training networks just to cope with these types of statistical variabilities in a data-driven way. On the other hand, there's also sort of much more geometric and well-structured types of variabilities that come up when you're thinking about invariant classification or invariant computing with image data. So one that I'm highlighting on the bottom left here is sort of geometric variability in the pose of an object, which is just arising because of the fact that natural images that you're maybe using or taking here of a subject, sort of subjects move around in the scenes that we're sort of capturing in these 2D images. And so as a result of that continuous motion, you have sort of a continuous geometric structure associated to the different images shown here of the same face. So this is the type of geometric variability. Maybe pose variations are one of the most common, but there are also sort of other sorts of structured, well-structured variabilities, maybe associated with illumination as well. And all of these give rise to a concrete low-dimensional structure, maybe associated to families of images of a common subject or a common scene. So one maybe natural approach to, in deep learning practice, to working with these or computing with these types of variabilities in order to have invariance is still maybe a data-driven approach where we use something like data augmentation, taking known images in our training set and augmenting them with structured transformations, not always this complex in terms of pose changes, but maybe these sorts of contrast or illumination changes to the image, just enlarging the data set in order to encourage whatever models that we train on this data to be invariant to these types of variabilities. So this sort of low-dimensional reckoning is present in, even this very fundamental operation of data augmentation, but we can highlight some pitfalls associated with just this purely data-driven, perhaps reckoning with this type of low-dimensional structure. So probably most of you are familiar with adversarial examples in neural networks, where it's sort of there's this phenomenon that it's possible to make imperceptibly small perturbations to an input image for a deep neural network that's maybe been trained to do image classification, and due to the sensitivity of the network to the input, have the predictions change in a sort of wild way from the true class to the wrong class. So what I'm highlighting here is an even more fundamental issue than sort of these worst case adversarial perturbations, where commonly trained neural networks can be susceptible to maybe pixel level translations of images that are in the training set. So on the top row here, we're translating an image that the network classifies correctly by a few pixels in either direction, and seeing that the sort of probabilities associated with the correct class can plummet. And the same sort of thing is shown at the bottom, where we're having pixel level scale transformations of the input image. Then nonetheless, although it's totally imperceptible to us, these simple geometric structured transformations that we encourage invariance to with data augmentation and things like that still end up in a lot of commonly trained neural networks having these sorts of stability issues. So robustness in neural networks, invariance as well, is very linked to, through this example and other similar ones, low-dimensional structure that's present in the data. And it's important to keep that in account to have these types of desirable stability properties. So the next example I want to spend a little bit of time talking about is drawn from a slightly different application, but still very important, scientific discovery. And in particular, one application that I learned a little bit about during my PhD was this gravitational waves problem. So this is a case where we're trying to verify predictions of certain physical laws by taking some measurements of astrological phenomena, astrophysical, phenomena that are occurring in the universe. What's happening here is that there's an event, a black hole merger. When these two black holes merge, just based on sort of predictions of the laws of general relativity, there's a relatively small number of degrees of freedom associated with this system. And as a function of those degrees of freedom, certain gravitational waves are emitted, and those can be sensed with detectors on Earth that folks have constructed, at least in the USA. So the types of signals that you're getting in this application associated with an actual gravitational wave merger are shown at top left or top right here on the slide. It's kind of a chirp-like signal. And if you sense many different merger signals, just because of the fact that you have a relatively low number of degrees of freedom that parameterize the variability of these signals, what you end up getting is that the observations here follow the structure of a low-dimensional manifold, just parameterized by those degrees of freedom that are sort of characteristic to the physical signal. And so one very basic task that folks might want to solve in a problem like this is just detection. So trying to figure out whether an observation that we've obtained on some of these detectors that we've built contains a gravitational wave event or not. So this is sort of a very simple classical statistical problem just associated with deciding between sort of signal plus noise or pure noise. If we can have these detection events, then we can sort of process this data, make sort of inferences, predictions on the underlying physical laws of the universe, and interesting questions like that. But there are already some sort of interesting issues that pop up and even thinking about this type of a problem from the deep learning perspective. So one way you can perform detection here that's very classical is just to use kind of a template matching approach or a matched filtering. So because we have this sort of parametric flavor in the problem here, we have a small number of degrees of freedom that parameterize the variability of the signals that we're sensing. What we can do here is collect a lot of different templates associated with some physical model of the signal. That's the gamma parameter here, maybe capturing the masses in the previous slide. When we have some new data, we can filter that data against these templates. And if we sort of choose a threshold properly based on information theoretic criteria, we can decide that we have a detection or not when sort of a filtering exceeds a threshold. But issues that come up here, sort of things that you might like to do. So in the context of deep learning, there's a lot of unknowns in this system that you might want to compute or treat in a data-driven way. So for example, there are very complex noise processes that lead to corruptions in these observations. You might want to be able to use data-driven approaches using deep learning to cope with those. Even just talking about simple issues like optimality of the statistical test in general. So I guess this is known in classical dating back to the 60s, but it's easy to forget in the modern deep learning era. This type of a simple parametric template matching test is not optimal. And to get a better test, you might want to be able, or working in sort of a data-driven way. This operation that we have here is the sort of template matching is very similar to one layer in a deep neural network, doing a lot of linear filtering operations and then taking a max, kind of like a pooling operation. It sort of stands to reason that with that similarity, maybe swapping out the detector here for a deeper network would allow you to do better in these issues of optimality, even efficiency as well. How many filters do I need in order to accurately detect? But the current practice here is very much on the science side, sticking with the sort of brute force template matching approach, just due to its simplicity and interpretability. If we can understand better the interactions between the deep models that we're sort of computing with on the internet scale and actual data that has concrete low-dimensional structures like we're seeing in this example. So we can potentially have a big impact in scientific discovery problems like this as well. So the third example that I'll talk a little bit about and that we'll see much more later in the afternoon is the issues of sort of computing good features from data in a self-supervised or unsupervised way when we're using deep learning and trying to understand how those features behave. So one workflow that's very common these days is to sort of do some kind of a self-supervised training, or maybe a training on a certain benchmark data set, maybe training a deep neural network to on a large benchmark like ImageNet, and then taking the weights of that deep neural network. And when we want to solve a specific task downstream, maybe in computer vision doing some tracking or segmentation task, we'll take those pre-trained weights and then fine-tune them on data from our specific application in order to optimize performance for that specific task. And the idea here is that when we can pre-train on these very large internet scale data sets of, say, images, we can extract good representations from our data, which are very useful for various downstream tasks that we might want to solve. And so issues that come up here, we might want to understand sort of in connection to the dictionary learning problem that Yuchen told us about in the previous talk. Can we actually get an understanding of what features are learned here, why they're good for these specific tasks, how they reflect structure, different types of structures in the data? And even more so when we have that specific knowledge, maybe like, for example, in the Gravitational Waves application where we know a little bit about the physical model that we think generated our signal, how can we incorporate that into the neural network that we're using to compute with these data, maybe to do a bit better performance-wise or efficiency-wise? So these are, I think, very active areas of research, and throughout the workshop, we'll actually hear a lot of research talks around problems much like this in feature learning as well. This is sort of an area where understanding is evolving very quickly, but it's also one that's very intimately connected to low-dimensional structures. So what can we maybe pull out from these three vignettes as maybe a common thread to build off of? So the two things that I pull out here, the first is that nonlinearity in sort of the data that we're computing with in these deep learning applications is totally essential. So where deep learning is really maybe successful or needed, it's where we have complex nonlinear structures in data. And the flexibility of these nonlinear deep learning models is maybe in a large part useful for coping with these types of nonlinear structures in the data. That's one thing. And the other thing is that actually there are many important practical issues, especially robustness and invariance, but of course also efficiency and performance, maybe detection and things like that as well, that are linked to considerations about specific low-dimensional structures that are present in the data. So by getting a better understanding of interactions between deep networks and low-dimensional nonlinear data, we can get insights into these important practical issues. So in the next part of the talk, I want to say that maybe we've motivated enough, we have a good model here, and start to formalize a bit. So I'll talk a little bit about a specific mathematical formalization of a certain model for low-dimensional structure that's motivated in large part by the image classification task. And we'll try to do a little bit of analysis there. I'll give a high-level overview of some of the things that we can try to prove, understanding similar guarantees in terms of efficiency and resource trade-offs to what we talked about in the examples of sparse recovery. So before I do that, I want to just pause briefly and see if there are any questions about the motivation or the examples from the audience. If not, I'll just jump right into the next part. Okay, so especially inspired by the example in image classification, one thing that we saw there was that there's this very specific mode of variability of natural images associated with objects moving around, changes of pose, which are these sort of structured geometric transformations of an object in a scene. So these geometric transformations, because they have nonlinear low-dimensional geometric structure themselves, give rise, when we talk about maybe classifying between different images under these transformations, to problems where the main computational task is to classify between two nonlinear low-dimensional submanifolds of a high-dimensional ambient space. So the formalization we'll proceed with here is to say, okay, we have this geometric structure in practice. Why don't we model this as sort of a geometric manifold structure for our data? And so we'll try to understand what we call this multiple manifold problem, where you're solving a k-way classification problem of data where the classes are drawn from low-dimensional submanifolds of this high-dimensional ambient space. And we're trying to classify using a deep neural network. So more formally, here's some of the notation that we'll see throughout the rest of this part of the talk. We'll specialize to a simple case where we're looking at binary classification. And this gives us the two-manifold problem. So the task here is just the following. Given capital N IID labeled samples from some density that's supported on the union of two low-dimensional submanifolds of the unit sphere. Those submanifolds are going to be more or less arbitrary, subject to some constraints I'll talk about on the next slide. So those can be just very general geometric objects. Okay, so given those samples from this density, we're going to use gradient descent to train a deep neural network classifier, and we're going to try to obtain a guarantee that says that from gradient descent, we'll get parameters that give us a perfect separator for the manifolds. And so we want to understand conditions under which this is possible. So when I say perfect separator here, this is kind of asking for training on finite samples, generalization to unseen data in a pretty strong sense. So we perfectly classify all future data drawn from either of the two manifolds. So a few of the features here, again, just to highlight, this is just a binary classification task. So we're looking at sort of a simple ImageNet type inspired problem to get some insight here. We have sort of a latent or unknown low-dimensional structure that's present in this model. The data is high-dimensional. You can think of the ambient space here as kind of representing pixels in sort of an image. The low-dimensional structure is just the degrees of freedom parameterizing the intrinsic variability of the data. And we're sort of going to prove a generalization guarantee after training on finite samples here. And so the constraint that I'll look at here, or that I'll enforce, is rather than talking about general d-dimensional manifolds, we'll just look at one-dimensional submanifolds. And these will be asked to lie in the unit sphere. So one-dimensional submanifolds are just curves, like kind of is shown or sketched in the figure here. And so this is maybe the simplest possible example of a pretty general class of nonlinear, low-dimensional geometric structures for data distributions. We're going to try to understand resource trade-offs here. So in analogy to what we obtained for the example of sparse recovery, we can try to set ourselves a goal here of what we want to understand and what types of guarantees are going to be appropriate, and maybe what are the central issues that we're playing with here. So in the case of compressed sensing sparse recovery, where we're doing reconstruction of a sparse signal from linear measurements, we had guarantees that told us when we collect a sufficiently large number of measurements here, where that sufficiently large is relative to the intrinsic structural properties, here the sparsity of the data, then we can efficiently reconstruct. So if we have enough sort of measurement resources relative to the intrinsic structural properties of the data, efficient reconstruction is possible. And so the questions we want to ask in this sort of mathematical model for deep learning are, what are the corresponding measurement resources? So presumably they're associated to the properties of the neural network architecture. And also, when we have this nonlinear low-dimensional geometric data, what are the intrinsic structural properties that are going to govern whether it's easy or hard to learn to classify data from the two manifolds? So we'll dig a little bit into first the issue of the intrinsic structural properties of data that are going to play a role in parameterizing difficulty of an instance of the two-curve problem here. And so we're going to see in the analysis that we look at here, just 3 parameters, more or less, can allow us to summarize difficulty. So we have kind of a separation parameter, a margin type parameter, a curvature parameter, which we're going to see is governing sort of regular or irregular, each individually the 2 data manifolds are, and some kind of a complicated separation frequency parameter, which we'll talk a little bit about, and just is governing how many times the data can tend to loop back on itself. So first, just this separation parameter. Like I said, this is a lot like a margin parameter in classification problems, but in this geometric data model, the 2-curve problem that we're looking at here, this is measuring sort of what's the minimum nonlinear distance measured through walking in the extrinsic space. So our curves lie in the sphere here. That's the extrinsic space. And what's the minimum nonlinear distance between a point that crosses the 2 curves? So in the figure here, kind of in the top right, there's a small deep purple line that marks the minimum distance in this sort of 2m's configuration between the 2 curves. So this is intuitively measuring how difficult it is to separate the 2 data distributions. And we're going to assume in the analysis that this is a positive number. So the separation is important. We also have sort of a curvature parameter. Because we have this nonlinear geometric structure, now we need to measure sort of what is the deviation of our data manifolds from being kind of the ideal not curved flat structure. And this curvature parameter that we define on the slide here is capturing that. So intuitively, for this sort of definition of the extrinsic spherical curvature of a curve, a one-dimensional manifold on the sphere, this quantity is going to be equal to 0 for the analog of a subspace or a flat data distribution. So that's just a subspace intersected with the sphere. And in the one-dimensional case, that'll be a great circle, just a sort of hemisphere of the sphere. In that case, we have 0 curvature. And we have maybe in the sense of curvature, a very benign data distribution. In general, though, when you have curvy data like these 2m's, the curvature can be quite large. In the figure here, we're marking the point of maximum sort of worst case curvature over either of the 2 data distributions with this little pink oscillating circle. So 1 over the curvature is equal to the radius of that circle. When the data tends to sort of, the data manifold moves quickly, loops quickly in that sense, you have a higher curvature measured through that radius being small. Question? Yes, good question. Exactly, yeah. So this X here is implicitly reflecting a parametrization of the data manifold. So we have like just a parametrization of the curve, and the double dot means the second derivative of that parametrization in, kind of the arc length sense, walking along in that parametrization. For curves, this is kind of canonical, so we can always have such a parametrization subject to some technical assumptions which are really quite general. But that's what the double dot means. And then the other things appearing here are just x. This first matrix is kind of a projection. So this specific quantity here on the sphere, I can't remember if we talked about it in the previous talk, but on the sphere, the tangent space to the sphere is kind of, it's going to be perpendicular to the radial component of a point on the sphere. So if this is the surface and this is 0, the tangent space will look like that. And this matrix here is projecting into that tangent space. So it kills any component of the curvature of either of the data manifolds that's going parallel to the current point. That's why I call it an extrinsic curvature of the sphere. Does that answer the question? Thanks. Okay, so curvature, separation, and the third parameter that we need in order to talk about complexity here is this Clover number parameter. So we'll call it the Clover number. This is capturing intuitively the tendency of either of the data manifolds to loop back on themselves or come close to a point on the other curve a large number of times. So while you're parsing maybe the formula here, I'll just talk intuitively about what this parameter, what we feel like it measures, maybe for practical data. So again, thinking about the example of very simple image transformation manifolds. At the top right here, I'm showing you some t-SNE embedding, so heuristic, but hopefully representative, of data that's obtained by taking an MNIST digit, so at the left a 4 and at the right a 1, and taking all possible rotations in the plane, so by angles from sort of 0 to 360 degrees of that digit. So that gives me a bunch of images, and then I t-SNE those to get a low-dimensional representation of the variability. So what we end up seeing with the 4 is that when we embed, this data tends not to intersect itself. Whereas for digits that are self-similar, like the 1, so it has a symmetry under, or an approximate symmetry under rotation by 180 degrees, we tend to see in the t-SNE embedding a self-intersection around halfway through the, along the way of the parameterization once we've sort of embedded in the low-dimensional space. So this Clover number parameter that we define here, which intuitively counts the number of times that the data can loop back on itself, is going to be higher in this example of image transformation manifolds for data that is self-similar, so data that has certain symmetries. Like in the digit case, we have this symmetry under reflection by 180 degrees. So intuitively, for practical data, data that is coming from image transformation manifolds or data coming from maybe physical systems, we probably don't expect this sort of a self-intersection parameter to be too large. But when we go through the math, it's important to have a precise accounting of what it is for the types of guarantees that we get. Again, this is just counting we have this separation parameter, which is determining the minimum distance between the opposite curves. This is counting how many times we can actually come back to a neighborhood that's at that sort of resolution of that separation. So that gives us these three complexity parameters, intrinsic structural properties of nonlinear low-dimensional data, that in this two-curve problem that we're studying here are going to allow us to parameterize the difficulty of an instance of the problem. So it's interesting to note here, maybe there's an analog somewhat of the separation when we talk about sparse or other sorts of bilinear, et cetera, non-convex models. But a lot of these parameters here, especially the curvature, these are truly nonlinear that only sort of show up in problems when we actually go to model the sorts of nonlinear structures that we think are present in a lot of deep learning applications. So in that sense, they're capturing that unique aspect of the data in these types of problems. So next, let's talk about the neural network that we're going to use, the algorithm gradient descent that we're going to use to train, and get those details out of the way. So in this discussion, we're just going to consider a very simple, very generic neural network architecture that's nonetheless flexible enough to allow us to talk about some trade-offs. So we're going to work with a deep feed-forward ReLU neural network. The depth is going to be L, the width we're going to call N. All the layers have the same width. We're going to consider gradient descent training from a Gaussian random initialization done in kind of the standard fan-in or PyTorch format. All the weights of the intermediate hidden layers are going to have sort of 2 over width variance, and that 2 is just a parameter to guarantee stable propagation throughout the neural network. And the training that we're going to do is just very simple, sort of classification as regression, training on the empirical mean squared error evaluated over these capital N IID labeled samples that we have from the unknown density supported on the union of the two data manifolds. So this mu will be the sort of measure associated to that density rho. So just recapping or going back to this analogy between the example of sparse recovery, now in the sort of nonlinear deep learning setting that we're trying to model and study here, we have the sort of nonlinear structural properties of the data that are representing our intrinsic structural parameters, maybe a little bit analogous to sparsity in the familiar case. And we have these architectural resources associated with the neural network, sort of in analogy to our measurement resources in the sparse recovery case. So those architectural resources are going to be in our analysis, the width of the network, its depth, and the number of samples that we get from the two densities. And we're going to try to understand this issue of resource trade-offs here. How do we need to set the resources of the neural network, the architectural resources, statistical and sort of architectural, relative to these structural properties of the data? How complex is an instance of the two-curve problem, so that we can guarantee success with gradient descent training? This is the question we're going to try to study, answer at a high level in the rest of the talk. So let me talk a little bit here, going into some of the details of the analysis and how we can sort of maybe start to prove some types of guarantees for neural network training, even though the optimization problem is highly complex. So the square loss empirical objective, we can write it in this kind of arcane form, which is sort of useful for analysis. This is the objective we're minimizing as a function of the neural network parameters theta in our training. And we want to prove that gradient descent on this loss can give us parameters that are going to yield perfect separation of the two manifolds. So one approach we might try to take here, which is sort of analogous to what we were using for the convex and non-convex toolkit that we talked about in the first two lectures, is to understand the geometry of this objective phi, maybe using considerations about the symmetries associated to the neural network architecture that we've selected, this deep feed-forward network, in parameter space. So an explicit understanding of sort of the theta side geometry, like what we use to analyze problems like matrix factorization, deep learning, sparse blind deconvolution, in which we've gotten a lot of mileage out of in the last 5 years. So this, I think, is, although there's always new and interesting progress for neural networks, this is extremely hard just due to the level of sorts of complex, non-convex interactions between the parameters associated with different layers of the neural network. And so in this talk, we're going to use a kind of different approach to look at the analysis of the neural network, which is to consider simpler dynamics. What I mean, we're going to analyze this objective from kind of a different perspective, just considering dynamics in input-output space. That is to say, sort of a kind of aggregate evolution, not of the parameters themselves, but of the prediction function that's implemented by those parameters. So that's going to be the evolution of the neural network's output, f sub theta on an input x, and a quantity that's going to play a big role in the analysis, which very naturally governs this evolution of the prediction function, is the so-called neural tangent kernel, which we'll talk exactly on the next slide about how this arises. But intuitively, this kernel is just an inner product between gradients at some parameters of the neural network function, evaluated at two distinct data points. And in that sense, it's measuring intuitively how easy it is to adjust the neural network's output at one point x without changing it at x prime. And in that sense, we can have the intuition, which we'll talk much more about in detail later on, that we want this kernel to be very sharply sort of peaked around the diagonal where x is equal to x prime. If it's small, when those two inputs are distinct, we can make rapid sort of gradient updates to our parameters. We'll see that in detail on the next slide. So to do that, I need to introduce a little bit of a notation. Forgive me. So two things we'll see throughout the rest of the discussion here. We're going to call this signed error zeta. That's just the difference between the neural network at some parameters. And so in particular, for most of it, we'll be looking at the random initial parameters of the neural network. You can think of theta most of the time as just that. So the difference between that neural network at random initialization and the true label function for those two manifolds. And the algorithm will use a sort of idealization of the constant stepping gradient descent, which is just going to be a simple gradient flow, kind of just a continuous time analog, ignoring some technical issues, which we can always sweep under the rug and then resolve. This is kind of a continuous time analog of the constant stepping gradient algorithm on the parameters. So we see kind of in the sloping form that this this error function, the learned predictor minus the labels, evolves according to this neural tangent kernel. And it just comes through, a very simple calculation here. So this first equation is just dotting with respect to t. This is sort of the directional derivative. If we plug in the definition of the gradient flow for this theta t dot, we get an equation like this. And if we manipulate it a little bit, we end up seeing a certain integral operator arises very naturally, which involves this neural tangent kernel, the inner product between gradients. So the integral operator here is associated to the empirical measure coming from our finite sample from the data distribution. And so if we write that compactly, what we have sort of as a bolded integral operator, kind of analogous to a matrix that collects our different neural tangent kernel evaluations at the different capital N sample points in our data set, we end up with this very simple integral equation, or you can think of it as a matrix equation, that describes the evolution of the error throughout gradient descent training of this neural network at all points across the two manifolds. So this becomes significant because of this very interesting observation, to my knowledge, originally from these folks, Jacot et al., which is that you can actually analyze, so this, this complex dynamics that really governs the error evolution here. It's complex because this integral operator, bold theta, has a time component. So it actually changes with time. It changes in a complicated way that reflects both the random sample from the data distribution, this mu sub n, and also the specific evolution of the parameters of the neural network theta t, because this neural tangent kernel operator here that arises is evaluated at the iteration t parameters of gradient descent. So that sort of hasn't solved our problem of needing to analyze complex aspects of the landscape, the geometry of this objective as a function of parameter space. But what's interesting is that when you over-parameterize the neural network enough, when its width is very large relative to various architectural aspects of the network, and you have a large number of samples. So it turns out that this complex integral operator theta t is very close in a very strong sense, kind of an operator norm sense, to its random, its time zero, so at random initialization, expected value, so averaged over the weights value. So this is now a deterministic kernel, this theta, that doesn't depend on time. And once we actually perform this swapping out, we get a much simpler dynamics, which still implies guarantees for the original one, which is just a linear time invariant system. So this error in this auxiliary, maybe nominal dynamics, is just evolving according to a fixed matrix or a fixed integral operator theta. And now we can actually prove guarantees about the norm, say, of the error, which is going to allow us to control the generalization error in this problem, just using sort of reasoning about aspects of linear systems. So relationships between the initial error and the eigenfunctions and the eigenvalues of this integral operator theta. We'll get rapid decay, fast generalization error from gradient descent when we have a good alignment there. So the challenge here technically is just that in order to prove that we have alignment, when we have sort of nonlinear low-dimensional models for the data, it's very hard to argue that explicitly because there aren't any closed form expressions available for the eigenfunctions of this integral operator for general nonlinear low-dimensional geometries. And even if we do have those expressions, it's sort of a massive lift in terms of calculation in order to prove something. So the approach that we use in our analysis is to be a little bit more implicit. And so we didn't get to go into all the details, but I'm sure most of the audience is familiar here with maybe the dual certificate construction of optimality in sparse recovery and compressed sensing. So in a sort of homage to that theory, we're going to, in this nonlinear case, call a function g defined on the manifolds a certificate if it satisfies two conditions. One of them, and this is kind of capturing implicit alignment with good sort of low, large eigenvalue eigenfunctions of this integral operator. So if we can integrate g against this neural tangent kernel theta operator and approximately in a mean squared error sense reproduce the initial random error. And we can do that with a function g, a certificate g, which has small norm. So then if that's the case, then g will be called a certificate. Let me just say intuitively what is going on here. You can think of this g, since it's a function defined on the two manifolds, and what I'm actually plotting here is a numerical rendering of a certificate for this running example of two m's that we've been looking at in the talk so far. So the certificate here, it's actually a function on the two manifolds, and it sort of encodes through its sort of local global properties, kind of local variations, global things like like its height, the complexity of classifying the geometry. So I'll talk a little bit more about that later on, but you can see here that the certificate shown in purple is kind of larger in magnitude at points where the manifolds are closer. We saw the purple line earlier in the talk, and also a bit larger at points where the curvature is high. So in that sense, it encodes difficulty of the classification problem. And maybe in sort of a familiar way from the compressed sensing perspective, we can talk about in kind of an algebraic way, this certificate is guaranteeing that the initial error, the zeta, I didn't write it, but zeta is on the left-hand side of this mean square relation up above. This zeta is going to be close to the stable range of this random initial integral operator theta if a certificate exists. This is sort of implicitly guaranteeing that most of the energy of zeta is concentrated in the high eigenvalue eigenspaces of this integral operator. That's what I mean by the stable range. So two perspectives through which this certificate is helping us to implicitly reason about the difficulty of the classification problem and to be able to prove generalization. And I won't talk about any technical details, but just a small lemma and a little bit of scaffolding allows us to conclude that if a certificate exists, so satisfying the conditions up above, suitably made quantitative, then we're able to decrease sort of this L2 error, this generalization error of the predictor fairly rapidly as a function of different architectural properties of the data. So a certificate existing is going to be sufficient for us to guarantee that we generalize and that we get a result for the two manifold problem. So in the rest of the talk, I want to dig a little bit into, now that we're sort of armed with that understanding of how we can get a theoretical result here, what are some of the main resource trade-offs that play a role in whether or not we succeed in this classification problem? And specifically, so how do the architectural and statistical resources in the problem, the network's width, depth, and samples, play a role in governing properties of theta, ensuring that a certificate exists? And also, how do we have sort of an interaction between this operator theta and the geometry of the data? And so two sort of foreshadowings, what we'll see here is that the depth of the neural network is going to play the role of a fitting resource. So we'll see that when we have a deep enough network relative to the geometry, we'll guarantee the certificate of small norm exists, satisfying the conditions that we need. And the width is going to play the role of a statistical resource. When the width is sufficiently large, the network is sufficiently over-parametrized, we're going to tamp out statistical fluctuations associated with the random initialization and to some extent the gradient descent dynamics. And that's going to allow us to have sort of good control of all this random operator theta around its expectation and allow us to replace the complicated random process with a more simple deterministic one. So first, let me talk about just the key insight that comes from depth here. So if we talk a little bit, we haven't looked into it yet, but if we actually do some plotting of this neural tangent kernel theta that's associated to our Rayleigh network, we see something that's pretty striking. So this kernel, just by virtue of the Gaussian initialization, theta is a rotation invariant kernel on the sphere. So I can get its value evaluated in any xx prime just by picking one reference point and looking at how it looks there. So that's what I'm showing in the plot at the right here. This is a profile around the North Pole of a suitably scaled version of the expected infinite width neural tangent kernel theta at a fixed depth 5, sort of suspended over the sphere. And what you see is that, so sort of in a way that's desirable for the types of guarantees we want to establish, this kernel is localized around 0, and it kind of decays as we move away. So that's good because, as a reminder, this neural tangent kernel is governing our ability to adjust the network's output at distinct input points. If it decays fast, that's a good indicator that we can do what we need there. then the interesting effect that we see is that when we increase the depth of the neural network, this kernel gets sort of more sharper and more localized around its value at 0. So this is stepping up now to a depth of 625, where the kernel, at least at this resolution, kind of looks like a very sharp point just around the initial value. So what that means is that by increasing the neural network's depth, we can make this kernel sharper and sharper. We can give since this kernel is connected to the dynamics of gradient descent, that gives us a better ability to fit complicated functions. And in particular, when we make the sharpness, the level of sharpness of this kernel sufficiently large relative to the geometric complexity parameters of the data distribution in the problem, so things like the curvature and the minimum separation between curves, we can guarantee that a certificate will exist for the specific instance that we're studying. In a slogan, we have deeper networks fit more complicated geometries. And just to show you a little bit maybe of a simple illustration of the last claim, that we can decrease the size of the certificate by increasing the depth. This is just a very simple numerical experiment following along from the example shown previously of the certificate for the 2M's geometry. So what I'm showing it right here are two traces, unrolled, or kind of, I guess, unwrapped versions of the certificate's sort of trace on both the plus curve and the minus curve. So left is going to be plus and right is going to be minus. And the different warmths of green coloration of these different traces shown in each plot are representing sort of the magnitude of the certificate for different depths of a kernel. So what we see here is that actually the magnitude is decreasing in a pretty strong sense as we increase the depth of the neural network from 1 or 2 to 10 to 100. It's going down kind of an octave for each increase in depth. And something that doesn't, you may see if you squint at it a little bit, is that there's a fairly pronounced improvement in the size of the certificate when we go from a very small depth, like 2, to a larger, a depth around 100. So we have some kind of diminishing returns with respect to depth as it gets larger and larger and larger. There's something, but it's a little bit diminishing. But the fact is that for small improvements, once we pass that threshold where the depth is set appropriately relative to things like the separation between the curves, their curvature, we actually get a fairly significant improvement. So that's the main effect in the analysis that is allowing us to guarantee the certificate of small norm exists by increasing the depth. And again, this is just a simple numerical illustration that this really does play out in, at least a simple example of a geometry here. Next, I want to talk briefly about the role of width in the analysis, tamping out the statistical fluctuations. So what we're illustrating here is just, so the main role of width in our analysis is to control the fact that when we randomly initialize the neural network parameters to theta 0, these Gaussian initialization, they induce a very complicated process, random process, but still quite complex, associated to the gradients of the network that defines this neural tangent kernel operator theta. So the main task that we have for the width here is to understand, so how does adjusting the width control the statistical fluctuations of that random process around its sort of expectation. So what we're showing at the right here is kind of a trace of just a single sort of sample trajectory of this random process for some fixed x and the x primes that kind of move along a great circle going away from them, of this expected neural tangent kernel and various random instances of it at finite widths. And so what we see from this intuition is that as the width is increasing, we get more and more bounded fluctuations around this infinite width value, kind of shown as the nominal sharp curve in green in the middle. So as the width is larger, we get better concentration around the infinite width expectation of the neural network. Another role that the width is playing in the analysis that we won't touch into here because it's more technical is that neural tangent kernel aspect of things, which is guaranteeing that the actual integral operator theta t that governs the evolution of the error throughout training is actually changing with time. So in practice, we also need to make the width pretty large relative to other polynomials in sort of the network architectural parameters in order to guarantee that that change is small. That ends up setting a lot of the very messy rates in the analysis and rates that are associated in general with this type of neural tangent kernel approach to analyzing neural networks. And there's going to be a lot of research talks, I think, throughout the week about approaches that in maybe simpler cases can get around those sorts of unsavory dependencies, give you better efficiencies, provable efficiencies for neural network training. But with the neural tangent kernel approach here, and again, I'm not going to go into too much more details on that, but we also need to have overparameterization in order to guarantee that lack of changes to the neural tangent kernel throughout training. So the type of result that we can prove for the concentration of the initial random neural tangent kernel around its expectation is something like shown here. So when the width of the neural network is growing like a sort of linearly with the depth of the neural network, plus polylog factors in the depth, the ambient dimension, as well as maybe the sort of dimensionality of the manifolds, then we have sort of uniform concentration, kind of a strong subnorm concentration of this random process around its expectation. And so that allows us to effectively replace the initial random neural tangent kernel with its expectation and analyze that when we do the certificate construction part of the analysis of the dynamics. So what we end up getting here through this guarantee, through this linear dependence of the width on the depth, is that we're going to make our network wide relative to how deep it is, and that depth, again, is reflecting how complex the data is. So this is how the resources of the neural network need to be set relative to the structural properties of the data in order to guarantee success here. So the last aspect that we'll talk about briefly is the statistical resource of the number of samples we need to guarantee success in the problem. So here I'm just showing a simple case for that illustrates kind of the basic trade-off that we have here. So intuitively, we're minimizing the empirical mean squared error on our n sample points from the data distribution. So these two traces here are kind of illustrating what we expect to get here from this analysis I've described earlier in the talk around sort of the linear time invariant system governing the evolution of the error, is that at all the sample points, so since those are part of the training objective, we're going to get a small error, sort of in squared magnitude. And we're going to, in order to argue that we generalize, we're going to need to guarantee that this error is not getting too large when we move away from those sample points. So generalization is asking us to have a small error everywhere on the two manifolds, in particular in order to guarantee that we have this sign threshold consistency of the classifier. The error needs to be less than 1 in magnitude. So just guaranteeing that we have minimization at these finite sample points is also implying the error is not too large away from them, is going to allow us to generalize. And the way we end up doing that in the analysis is just using the fact that, again, when we're training in this neural tangent kernel regime, the dynamics of the evolution of the predictor, the zeta function, kind of evolves according to a kernel dynamics. So what that means is that there's a very characteristic shape that you can associate in a worst case sense to the deviations of this error function as we move away from the sample points, as we train for long enough times. And that characteristic function is really governed by just the shape of the neural tangent kernel. We were talking before about how this shape is governed by the depth, and deeper networks lead to a sharper, more localized kernel. The flip side of that is that when we localize more and more the kernel, now our error can grow more and more as we move away from our sample points. So what that means is that in order to guarantee generalization here, we just need to have a sufficiently large number of samples relative to this kernel aperture parameter, this sharpness localization aspect of the kernel. So functionally what that means is that the number of samples needs to be set according to the depth, since we talked about how the depth is what determines the sharpness of this kernel. So eventually, in the result that we're going to establish, we'll have a dependence of the number of samples for success on the depth of the neural network, just governed by this aperture of the kernel. And so the type of result that we can end up getting is going to look something like this. So for sufficiently regular one-dimensional manifolds and ReLU neural networks, when we set the depth of the neural network relative to intrinsic structural properties of the data, when we set the width to grow as a sufficiently large polynomial in the depth, and when we have a number of data samples that grows like a sufficiently large polynomial in the depth, then after not too many iterations of constant stepping gradient descent, we'll obtain parameters that give us a perfect classifier for the two manifolds. So that gives us, although the rates here are not going to be totally sharp, a somewhat satisfying resolution to the issue of resource trade-offs in this two-manifold problem. So we've understood the role that each of the architectural and statistical resources in the problem plays in allowing us to succeed here, how they need to be set relative to structural properties of the data. And that's given us sort of an end-to-end analysis here where we can prove a result for neural network training that just can be stated in maybe half of a slide, subject to technical restrictions. So that's all for this part of the talk. Let me very briefly summarize the conclusions again and try to interest you in some of the coming attractions for this afternoon as well. So what we've seen here is that maybe one of the essential features of low-dimensional structure and deep learning in modern applications is that nonlinear low-dimensional variabilities in modern data sets demand the use of these flexible nonlinear deep models. And we can have some understanding using generic neural networks and a simple data model of what types of resource trade-offs play a role in guaranteeing success in certain model classification tasks between these structural properties of the nonlinear data and the deep neural networks themselves. So we're going to start to, as I alluded to before, later in the afternoon, open the black box a bit here. We're going to talk more about features that are learned in the weights of these neural networks during training on certain classification type tasks. And then we'll talk even more about design of deep neural network layers for seeking good representations of low-dimensional structured data and motivated by certain structures that you may know are present in some tasks. So that's all to come in this afternoon. Hope to see you guys back later on for that. And thanks for listening to my talk. I'll take any questions if you have them.
So this is very high level. Can I think of your results as sort of analyzing the NTK kernel under these manifold assumptions a little bit, or no?
Yes. Yeah. So I haven't gone too much into other aspects, but there's also kind of an optimization side of things. So the analysis is going to be specific to the case of using a deep neural network, because for us, we needed to use depth large to prove these types of guarantees that you described. So can we get some new guarantees as well for the optimization side of the neural network or the neural tangent kernel training? So it'll have those two components, if that makes sense.
Thank you.
A couple of questions. The first one is, what is the connection between the manifold separation problem and, say, the first vignette?
Yeah, that's good. I think if there is any connection, it's highly stylized. And maybe so, in that sense, the connection is one of motivation. So we were maybe motivated to consider this manifold separation problem by considering some very simple model problem for separation of image templates that are induced by certain types of geometric structures. Of course, when you get down into the details, this type of Riemannian manifold structure is not the correct one for working with image transformation manifolds. There are a lot of other issues, different variabilities like we alluded to in the first vignette, illumination changes, things like that, that will make this task of separation of positive delta manifolds not the one that you really run into when you talk about classification of distinct image templates. But if that makes sense, it's kind of one of inspiration, drawing the inspiration from that first vignette for the manifold separation problem.
The second question is about the significance of the problem. Do we really want to, I mean, in most statistical learning problems,
yes,
there are errors in classification.
Yes.
And what we want simply is a small generalization error.
Yes.
While here, the task is really to achieve perfect separation.
Yes.
And therefore, by definition, you need to have a margin before you start. And also the y was a deterministic function of x.
Yes.
As opposed to x comma y being drawn from a joint distribution. So
yes,
what is the significance of the problem?
Yeah, that's a good question. I think it's, for this work I've talked about here, it's extremely important to extend it to this case of noisy observations, a general distribution rather than just y of x, as you said. I think because, although I'm not getting into a lot of the technicality in this talk, I think the technical kind of scaffolding framework that we introduce in order to prove this manifold separation result can be useful for the general case as well. Although much more needs to be done to cope with noise, I think the basic analogy is that you can imagine replacing this function y of x that I've talked about here with the regression function in a more general classification problem, the conditional expectation of y given x. This is maybe not the most general noise model that you can consider, but I think it's a good step towards more realistic classification problems that you described. And when we think about it through that analogy, then the same type of formulation that I've presented here, this L infinity guarantee for generalization, it's not going to connect to generalization perfectly per se, but I think it does have an interesting statistical interpretation, maybe getting whether or not you can learn a well-calibrated predictor, a predictor that is getting close in L infinity to the regression function. It's not immediately clear here. I'm thinking through some of the connections these days, whether with this this approach that's described here, the neural tangent kernel approach, just the kernel approach in general, whether you actually have this type of a consistency property or a close enough to consistency property. But this is an interesting question that I agree should be explored in follow-up work. But I do think the framework is going in that direction, although I haven't presented with you sufficient details for you to make that judgment here.
And my last question is, in the vignette, it was sort of clear how there was a low-dimensional manifold.
Yes.
But in the theoretical results, what was the dimension and what was the role that that dimension plays in the result was not entirely clear.
Yes. So in what I've presented here in the analysis that we've done for this problem, we've only looked at the case of dimension 1. That's why we fixated on this figure with two curves that we're separating between. So in general, I think for the type of approach we have presented here, the kernel-based classification and things like that, we can expect some exponential unsavory dependencies on whatever dimension of the manifold we have, if we model that aspect of the problem as well. Maybe in practice we expect this dimension to be constant or something like that, but exponential is still going to be pretty unsavory. So it's interesting to think about whether other types of techniques or whether other types of data structures, say not just an arbitrary d-dimensional Riemannian manifold, but a data manifold that has some structure, factorized, hierarchical. There are some analogs in maybe subspace arrangements. Whether then we can have better efficiency guarantees using the same type of framework. That becomes an interesting question that could be more connected to practice. But the short answer is that, yeah, we've just fixated on the d equals 1 case here. Although in general, we do want to be extending to that setting.